Today, we are implementing Retrieval Augmented Generation in Java with Spring AI, the exact skill that most companies are seeking right now. While everyone's talking about AI, few developers actually know how to build enterprise-grade RAG systems. If you master this, you will become the developer who can actually deliver results with AI. I will show you how to load documents into a vector database using Spring AI and perform similarity search, the foundation of every RAG system. We're starting with document ingestion because without data in your vector store, there is nothing to retrieve. The implementation is intentionally simple. You will use your own documents, your own data sources, but the mechanics remain the same whether you're processing 10 documents or 10 million documents. Every company wants AI features, but raw LLMs hallucinate. They make things up, they don't know your business data. RAG solves this by grounding AI responses in your actual data. Think customer support that knows your product documentation, code assistants that understand your codebase, or financial advisors that reference real market data. Without RAG, you're limited to generic chatbots. With RAG, you build AI that actually understands your domain. Every company has documents, PDFs, Word files, presentations, knowledge bases. Companies are paying premium salaries for developers who can implement this because RAG bridges the gap between generic AI and business-specific intelligence. Now, in RAG, why do we need vector databases and not traditional databases? Traditional databases with search index find exact matches or exact keywords. They're not very helpful for semantic understanding. Vector databases store meaning, not just text. When someone searches how to reduce costs, it finds documents about expense optimization, budget cuts, or financial efficiency, even if those exact words never appear. This is why many AI applications use vector databases. They understand intent, not just words. Traditional search would miss 80% of relevant results. If you want to learn more about RAG and its architectures, you can take a look at my previous videos. Links are in the description. But to recap, RAG has 3 core steps. Retrieval, to find relevant documents from your vector database. Augmentation, combine retrieved context with the user query. And generation, an LLM generates a response grounded in your data. In this video and the next couple of videos, we are building all 3 components using Spring AI. The beauty is Spring AI abstracts the complexity while giving us these valuable patterns. Now, let's set up our vector database. Because we are building the foundation for a future RAG system, we need the database to support vector search. Spring AI has more than 15 options: Pinecone, Chroma, Postgres, Azure Cosmos DB, MongoDB Atlas, and more. The vector store interface in Spring AI abstracts the implementation. It provides a common API to interact with different vector database implementations. This makes your code portable across different vector stores. The vector store interface defines a few core methods. The add method is the one that we'll use today. It will take a list of document objects, an embedding client, usually it's configured behind the scenes or you can manually configure it. It generates embeddings for the content of the documents, and then these documents and their vector embeddings are saved into the database. The delete method allows us to remove the documents from the vector store based on their IDs. The simple similarity search method is a way to find documents that are semantically similar to a query string that we provide. The similarity search with a search request parameter is a more powerful version of similarity search. It allows us to specify parameters like the number of results to return, it's often called top K, a similarity threshold to filter results, and even more advanced metadata filters, depending on the vector store capabilities. I will show you how you can easily switch vector database implementations with Spring AI. Let's create a database in Pinecone. I already have 3 instances deployed on AWS in US East 1 in a serverless capacity mode. It was very simple to create one. Once we have our database, we can create an API key. We will need to use it in our Spring AI application.properties file. So make sure to save your API key and database name. Now we are ready to move on to the Java application that will use the vector database. You can use Spring Initializer to create a foundation for your project, to choose your Java version, build system, metadata, and dependencies. I will use my JetBrains IDE and walk you through the dependencies and packages that we need. I'm using Maven. In JetBrains, open your pom.xml file and ensure you have the correct Java version and add a line for which Spring AI version to use. We will be using a Spring Boot Starter Web to run the application, Spring AI Starter for OpenAI model, Spring AI Starter for Pinecone database, Spring AI Advisors module to work with the vector stores, and Spring AI RAG dependency as well. We will also use Spring AI Tika document reader to work with a variety of file formats, as well as Spring AI Transformers dependency. We will need all of these for our RAG application. So also don't forget to include the dependency management section with the Spring AI BOM. Now we are ready to move on to configuration. Our application.properties needs a couple of critical settings: OpenAI API key, Pinecone API key, and database name. There are a couple of other settings here. For example, the temperature setting you can experiment with to set the creativity of your AI responses. The ETL documents folder is a custom setting that we are using here to configure the directory where we're going to load files from. And similarly, we are defining the ETL documents load on startup that we can set to be true or false, depending on whether we want to run the document loading again. The first challenge in RAG is getting your documents into the vector store. Here is how the pattern works. This is our main application class, annotated with Spring Boot application, which is the standard for Spring Boot app. You will notice that we are auto-wiring a vector store. This is a key component from Spring AI, and it's an abstraction over the actual vector database that we're using. We also have a couple of value annotations here. Documents folder path. This tells our application where to find the documents we want to load. Load documents on startup. This Boolean flag controls whether the document loading process is launched and whether it runs automatically when the application starts. The real interesting part for getting our documents into the vector store happens in a method that's designed for a robust ETL from files, and there is another simpler one for quick experimentation with document loading. Let's look at the simplest way of adding documents to the vector store. Load documents into vector store. It creates a list of document objects directly in the code with hard-coded content and metadata. and then it calls vector store add documents, again, using the vector stores add method. This is great for testing out small, static datasets. Now, if we want to get the documents out based on similarity to a query, we need to perform a retrieval step. In this method, we use a similarity search capability of our vector store. Instead of just passing a simple query string, we are using a search request. This builder pattern allows us to specify more detailed search parameters. Query, here we set actual search query string that we want to find similar documents for. This query would be the input to the method. Top K is a common parameter in the vector search. It tells the vector store to return the top 5 or top K most similar documents to our query, where K is the number of neighbors to find, and build is the method that finally constructs our search request object. The method then simply iterates through these results and prints the formatted text of each retrieved document. In a full RAG approach that you will see in the next video, these retrieved documents would form the context that's passed to a large language model along with the original query. This retrieve documents from the vector store method is a great example of the retrieval part of RAG. Now, when we run this simple document loading and the retrieval for a query with the word spring in it, we will see the pulled up documents in the output with the similarity distance indicator and any tags. With this, we are ready to see how to implement an actual ETL with real files and add them to our vector database. This method, load documents into vector database, is responsible for reading documents from the file system, processing them, and then adding them to our vector store. First, it respects that load documents on startup flag, and if it's false, it skips the process. We define a list of allowed extensions like PDF files, docx, txt, md, and so on. And then we check if the configured documents folder path actually exists and is a directory. It's basic but an important validation. Now for the core logic. We use files.walk to traverse the document's folder path and its subdirectories. We filter to get regular files and then check if their extension is in our allowed extensions list. For each valid file, we create a file system resource and then use a documents reader. Apache Tika is a powerful library for extracting text and metadata from a big range of file types. Spring AI provides this handy Tika document reader wrapper, and tikareader.get gives us a list of document objects. The single file might produce multiple document objects. For example, a PowerPoint presentation could yield one document per slide. After reading, we enhance each document with some useful metadata. Its source URI, where it came from, and the file name. This is great for traceability later on. Once we have all the raw documents, we need to split them into smaller chunks. Large language models have context window limits, and vector search works best with focused, smaller pieces of text. Here, we instantiate a token text splitter. Spring AI provides this to help break down text based on token counts. We configure it with parameters like target chunk size, how many tokens we want per chunk, minimum chunk size in characters to avoid tiny, meaningless chunks, and a few other parameters to fine-tune the splitting. We then apply the splitter to our list of all raw documents. Finally, the crucial step is we take our chunk documents and call vector store add. This is that add method from the vector store interface that we talked about. This is where Spring AI takes over. Spring AI handles embedding generation automatically. It converts each chunk to vectors using our configured model. These embeddings, together with the original text and metadata, are then stored in the vector database through the vector store abstraction. The logging here is also helpful because it shows how many chunks were added and even some of their IDs for verification. So to summarize, load documents into vector database, finds files, uses Tika to extract content, splits the content into manageable chunks, and then uses vector store add method to embed them and save them. With this data loading functionality, we are ready to execute the app and see how it works. We're going to call the more extensive loading method that we've implemented. We run the application, and we see that the logs are saying we are skipping document loading. Remember, we had a flag in the properties file that we need to ensure is set to true to load documents on startup. This is what we need. When we rerun the application, we see that Tika Runner started the ETL process, found our files, split it into chunks, and added them to the vector store. And it's showing us the IDs of the documents that were added. You can see the detailed logs that are helpful to understand the process. We now have a fully working document loading logic with a vector store that we can build with. We've used Pinecone database as our vector store. At the beginning, I mentioned that with Spring AI, we can change our vector store without changing our core logic. I want to show you how it's done. We will use MongoDB as an example. With Pinecone, I created a free cluster to show you this example. With MongoDB, it supports vector search only with their M10 clusters, which is 8 cents per hour. From MongoDB Cloud Dashboard, you can click Create button that will teleport you to enter your cluster name, provider, region, and any tags, and so on. Then it asks you about connection authentication. For the purposes of this video, I'm going with a simple username and password. It also asks you where you are planning to connect to your cluster from. If it's a local environment, it adds your IP address to the allow list of connections. It takes 7 to 10 minutes for the cluster to be ready, so I'm going to speed up that part. Once the cluster is ready, next step is to get its connection string. They have a nice UI to get the right format depending on your language driver. We go back to our IDE, specifically to our pom.xml dependencies file. Our goal is to swap Pinecone for MongoDB, so we add the Spring AI starter vector store MongoDB Atlas dependency. In the application properties file, we are going to add Spring Data MongoDB URI pointing to the connection string and the Spring Data MongoDB database name. Make sure to build your project, and then as you see, none of the actual code is changed. Everything is the same as we left it. We run the application, and indeed, the documents are being processed and loaded as expected. When we go to our MongoDB cluster dashboard, we see our files, their embeddings stored in the database. Before you scale this, monitor chunk distribution. If average chunk size is too small, you can increase the target size. Test different file types. PDFs with images may need different handling than text files. You should version your chunks and add timestamps to metadata for document updates. You can batch large ingestions, process documents in batches to avoid memory issues. You can also handle failures more gracefully. Some PDFs may be corrupted, some Word documents are password protected. So remember that this simple pattern scales. The same code works for 10 documents or 10 million documents. The vector store abstraction means you can switch from one vector database to another without changing your code. In the next video, we will build on this example with the Question Answer Advisor, turning these search results into intelligent responses. Then we will cover the Retrieval Augmentation Advisor for more sophisticated RAG pipelines. And finally, the multi-query expansion for improved retrieval. So make sure to subscribe and follow to complete this RAG implementation. Thanks for watching, and I will see you in the next videos.
Your reality has changed. You're stuck in your career. You're either using AI or being used. Do you still believe success is guaranteed? You feel it's time to wake up. Old strategies don't work anymore. Welcome to the real world. It will never be the same again. You need to fight for your future. Learn to spot truth from lies. I will help you. Together, we will win.